60 million transformers, 400,000 kilometers of high-voltage lines, 12,000 satellites overhead, 300 submarine cables carrying 99% of global internet traffic. It is the nervous system of civilization. It is working right now as you listen to these words. The light in your room, the signal on your phone, the money in your account. All of this is electricity turned into habit, and all of this could be burned away in a matter of hours. With a single emission from the surface of the nearest star. We are not talking about the distant future. We are not talking about theory. We are talking about an event that has already happened, and which, according to calculations, will happen again. The question is not whether it will happen. The question is when. 150 million kilometers. That is the distance between the Earth and the Sun. Light travels this distance in 8 minutes. To human perception, it is an abyss, a void, a safe distance. But space does not know the word safety. The Sun is not a yellow circle from children's drawings. It is a thermonuclear reactor with a diameter of 1,400,000 kilometers. Every second, 600 million tons of hydrogen are converted into helium in its core. The temperature is 15 million degrees. The pressure is 250 billion atmospheres. This is a place where matter exists in a state that has no analogue on Earth, and this machine is unstable. The surface of the Sun is not a smooth sphere. It is a seething ocean of plasma permeated by magnetic fields of monstrous power. These fields twist, intertwine, and accumulate tension, like a spring that has been compressed for months, and then they release. The result is called a coronal mass ejection, 1 billion tons of magnetized plasma accelerated to 5 million kilometers per hour. A cloud carrying the energy of millions of hydrogen bombs, and if it is directed towards Earth, we have between 15 hours and 4 days to prepare, or not to prepare. The year is 1859. It is the 1st of September. It is a typical morning in the suburbs of London. An amateur astronomer climbs up to his private observatory, points his brass telescope at the Sun, and begins to sketch the dark spots on its surface. It is routine work that he has done hundreds of times before. At 11:18, the routine ended. 2 dazzling flashes of white light burst forth from the sunspot group. The observer rushed to find a witness, but when he returned 60 seconds later, the flashes were already fading. The entire phenomenon lasted about 5 minutes. The astronomer did not know that he had just become the first person in history to see a solar flare. He did not know that something was already flying towards Earth that had not yet been named. 17.5 hours later, this something reached the planet. The speed was abnormal. Normally, coronal ejections take 3 to 4 days to travel the distance to Earth. But a few days earlier, another, less powerful ejection had occurred. It cleared the way, displaced the solar wind, and removed environmental resistance. The second blow came down the open corridor. When the plasma cloud collided with Earth's magnetosphere, the most powerful geomagnetic storm in recorded history began. The planet's magnetic field shook. Auroras flashed where they had never been seen before, over Cuba, over Hawaii, over Colombia, right on the equator. The sky above the Rocky Mountains became so bright that miners woke up in the middle of the night and began preparing breakfast, mistaking the glow for dawn. In New England, people read newspapers on the street, without streetlights, only in the light of the blazing ionosphere. But beauty was only a symptom. That same night, the telegraph network, the most advanced technology of the era, began to die. The machines sparked, the wires burned hot, operators were electrocuted, some so severely that they were thrown from their equipment. Paper at the stations caught fire from the discharges. And then something happened that the engineers of the time could not explain. The telegraph operators disconnected the batteries, the power sources, but the machines continued to operate. The line between Boston and Portland transmitted messages for 2 hours straight, using only the current that flowed through the wires from nowhere, from the atmosphere, from the Earth itself. This was the first time humanity had encountered geomagnetically induced currents, GICs. These are parasitic currents that arise when the planet's magnetic field fluctuates under the impact of solar plasma. These currents seek the path of least resistance, and find it in wires, pipes, rails, in anything that conducts electricity. In 1859, humanity had 100,000 kilometers of telegraph lines. They broke down, and were back in operation within 12 hours. Today, the nervous system of civilization is hundreds of thousands of times more complex. and it is much more fragile. To understand the scale of the threat, one must understand one simple thing. Modern civilization is built on alternating current. Power stations generate it. Transformers increase the voltage so that it can be transmitted over hundreds of kilometers. Other transformers reduce it for cities, factories, and homes. This system operates at a frequency of 50 or 60 Hz. The current changes direction dozens of times per second, and the entire infrastructure is designed specifically for this. Geomagnetically induced currents are completely different. They are quasi-constant, slow. They flow in one direction, and this direction is deadly for transformers. When GIC penetrates the transformer winding, a phenomenon occurs that engineers call half-period core saturation. The magnetic circuit, the heart of the transformer, can no longer cope with the load. It begins to overheat. The windings become red hot. The insulation melts. The oil inside the casing boils. A transformer does not explode instantly. It dies slowly or quickly, depending on the current. But when it dies, replacing it is not easy. A high-voltage transformer is not something you can buy in a shop. It is a unique product weighing between 100 and 400 tons. Each one is designed for a specific substation, a specific voltage, and a specific load. It takes between 18 and 24 months to manufacture a single unit. Delivery requires special railway platforms. There are about 10 of them in the United States. 60 million transformers operate in the American power grid. More than half of them are over 33 years old. They have already exceeded their estimated service life. There is a critical shortage of spare units. The waiting list for new ones ranges from 80 to 210 weeks. This means one simple thing. If a geomagnetic storm knocks out several hundred key transformers at once, recovery could take not weeks but months or even years. But transformers are only the first level of vulnerability. Above our heads are 12,000 satellites. They provide navigation, communications, internet, military intelligence, weather forecasts, and financial transactions. They hang in space, protected only by a thin hull and the Earth's magnetic field. During geomagnetic storms, the upper layers of the atmosphere heat up and expand. For satellites in low orbits, this means a sharp increase in atmospheric drag. They slow down, they lose altitude, they fall out of orbit. In February 2022, a company launching satellite internet lost 38 of its 49 satellites. They burned up in the atmosphere a few days after launch. The reason was a geomagnetic storm of moderate intensity, not even a strong one. In the event of a Carrington-class incident, the count will be in the hundreds, possibly in the thousands. But even those satellites that survive may prove useless. Solar panels degrade under the flow of charged particles. Electronics malfunction from single events, when a high-energy particle switches a bit in memory, turning a 0 into a 1. One such malfunction, and a navigation satellite begins to transmit false coordinates, GPS, 4 letters that mean more than you might think. Precision farming, tractors with autopilot that sow fields with centimetre accuracy. Oil well drilling, a deviation of 1 metre and the pipe misses the deposit. Aviation, instrument landing in zero visibility conditions. Maritime navigation, synchronization of bank transactions, operation of cellular networks. In May 2024, during the last powerful storm, farmers in the Midwest faced a problem. Their GPS-controlled equipment began to malfunction. Tractors veered off their furrows, seeders missed patches. The losses were calculated in missed planting days, and in agriculture every day counts. And it was a G5 class storm, strong but not extreme. Its magnetic activity index was minus 412 nanotesla. The Carrington event is estimated at minus 800 to minus 1750, 2 to 4 times more powerful. Beneath the oceans lies another layer of vulnerability, 320 cables that carry almost all of the world's internet traffic. The fibre optic cables themselves do not conduct electricity, they transmit light. But alongside them run copper wires that power repeaters, signal amplifiers located every 50 to 100 kilometers. These conductors are vulnerable to GIC. The scientific community is debating the degree of risk. Some studies claim that the cables can withstand even Carrington. Their backup systems are capable of absorbing surges of up to 6,000 volts. Others claim that repeaters at high latitudes could burn out, leaving entire continents without communication with each other. The truth probably lies somewhere in between. But the very fact that scientists do not know the exact answer is already a diagnosis. We built a global infrastructure without testing its resilience. Suppose that tomorrow a Carrington-class solar flare occurs on the Sun. A massive sunspot, the size of Jupiter, ejects 1 billion tons of plasma into space, accelerated to 2,000 kilometers per second. The X-ray burst reaches Earth in 8 minutes. The first impact. The upper layers of the atmosphere become ionized. Shortwave radio communication on the sunny side of the planet goes dead. Pilots over the Atlantic lose contact with air traffic controllers. Polar flights make emergency route changes. Satellites in geostationary orbit detect a sharp increase in proton flux. Sensors reach saturation. A solar radiation storm begins. Deadly for astronauts, dangerous for high-altitude flight crews, and destructive for electronics. 12 to 18 hours later, the main impact arrives. The plasma cloud itself. It cannot be seen, it cannot be heard, but when it collides with the Earth's magnetosphere, the planet shudders. The magnetic field that normally protects us begins to vibrate. Lines of force are distorted, broken, and reconnected. Each oscillation induces an electric field in the Earth's crust, and this field drives current through everything that conducts electricity, along rails, along pipelines, along substation grounding circuits, along cables under oceans. The first transformers begin to overheat within minutes. Protection systems detect abnormal harmonics in the network, parasitic frequencies that should not be there. Relays trip, lines are shut down. In 1989, a moderate storm knocked out the power grid in a Canadian province in 90 seconds. 6 million people were left without power for 9 hours. The temperature outside was minus 15 degrees Celsius. Heating, traffic lights, water pumps, everything came to a standstill. The Carrington-class event will not be about the province. The East Coast, the Upper Midwest, Scandinavia, regions with resistive rock formations, those that do not conduct electricity well, suffer the most. That is where GIC looks for alternative routes and finds them in power grids. Cascade effect. One transformer fails, the load is redistributed to neighbouring transformers. They become overloaded. They shut down or burn out. The load is redistributed again. A chain reaction. In the worst-case scenario, rolling blackouts across the continent within the first hour. The lights go out, screens go blank, refrigerators fall silent. Pumps at petrol stations stop pumping fuel. ATMs do not dispense money. Cash registers do not ring up purchases. But this is only the beginning. Without electricity, water treatment plants do not work. After 24 hours, the pressure in the pipes drops. After 2 days, the water becomes unsafe to drink in cities that have not had time to switch to backup sources. Without electricity, petrol stations do not operate. Trucks that deliver goods to supermarkets come to a halt. Shelves become empty. Without electricity, cell towers do not work. Their backup batteries are designed to last for several hours, a maximum of 24 hours. Phones become useless pieces of plastic and glass. Without electricity, hospitals switch to generators. Generators need fuel. Fuel needs to be delivered. Delivery requires functioning petrol stations. The circle is complete, and above all this is the question that no one wants to ask out loud. How long will the recovery take? If dozens of transformers are damaged, it could take weeks, possibly months. If there are hundreds, it could take years. Economic models estimate the damage to the United States alone at between $600 billion and $2.5 trillion. Global losses over a 5-year recovery period could reach $9 trillion. But these figures are abstract. Behind them lies something more concrete. People without heat in winter, without cooling in summer, without clean water, without contact with loved ones, without functioning healthcare, without their familiar world. All this is not the plot of a science fiction film, it's physics, it's engineering, it's a vulnerability we created with our own hands. We've already seen the warnings, not in simulations, in reality. On the 13th of March, 1989, a geomagnetic storm struck North America. Its strength was 3 times less than that of the Carrington event, but that was enough. The province of Quebec, 6 million people, was plunged into darkness in a minute and a half, 90 seconds from the first failure to complete collapse. The transformers overheated, the protective relays tripped in sequence. The system, which had taken decades to build, collapsed faster than an announcer could read an emergency message. 9 hours without power, -15 outside, elevators stopped, metro frozen, traffic lights out, heating turned off. The damage amounts to $13 million in direct losses alone. Indirect losses are many times greater. In Sweden, the same storm knocked out part of the power grid. In South Africa, it damaged transformers at substations. And this was a storm with an index of -589 nanotesla. Strong, but not extreme. October 2003, Halloween storms. A series of powerful flares and emissions hit Earth over a 2-week period. More than 50% of spacecraft in orbit were affected. Malfunctions, loss of orientation, system degradation. A Japanese satellite worth $640 million was completely lost. Astronauts on the International Space Station took shelter in a protected module. Airlines rerouted flights from polar routes. Each turnaround cost up to $100,000. Northern Europe has once again experienced power outages. Sweden, again. And again, these were strong storms, but not the strongest. And then came July 2012, an event that almost no one heard about, because we were lucky. On 23rd July, a Carrington-class coronal mass ejection broke away from the surface of the Sun. 1 billion tons of plasma. Speed, over 2,000 kilometers per second. Power, comparable to that which struck Earth in 1859. The cloud passed precisely through our planet's orbit. But at that moment, Earth was at a different point in its orbit around the Sun. The difference was 9 days. 9 days, and we avoided a catastrophe that could have set civilization back decades. The satellite, which was in the line of fire, recorded all the parameters. The data leaves no doubt. If the launch had taken place a week earlier, it would have hit its target precisely. We did not prevent the threat, we simply did not stand in its way. May 2024, the last major event, a storm that was later named Gannon's Storm after the space weather researcher. The irony is that on that very day, NASA was conducting training exercises, a simulation of a solar catastrophe. 30 government agencies gathered to work through a what-if scenario, and in the middle of the simulation, the hypothetical threat became real. The first G5 storm in 21 years. The aurora was seen in Florida, Cuba, and Puerto Rico. Shortwave radio communications were interrupted across the planet. GPS systems malfunctioned. Agricultural machinery in the Midwest lost its course. However, critical infrastructure managed to avoid major damage. Power grid operators were warned. The load on the lines was reduced in advance. The transformers withstood the storm. This does not mean that the system is invulnerable. This means that with sufficient warning, with sufficient preparedness, damage can be minimized. The question is whether we will be ready next time. Humanity is aware of the threat. It is no longer a secret, a conspiracy theory, or a plot for science fiction. It is a recognized risk that is being discussed at the level of governments, insurance companies, and international organizations. And, slowly, reluctantly, but still, we begin to defend ourselves. 1.5 million kilometers from Earth, at Lagrange, point L1, satellites stand guard. They watch the Sun and warn of approaching emissions. The warning time ranges from 15 minutes to an hour. This is not enough time for evacuation, but it is enough for power grid operators to reduce the load, shut down vulnerable sections, and switch systems to protective mode. The European Space Agency is preparing a mission to L5, which will allow it to observe the Sun from the side and see threats before they turn towards Earth. Engineers have developed neutral blocking devices that cut off GIC direct currents, allowing only alternating currents, for which transformers are designed to pass through. The first such devices have already been installed at substations. Regulators require operators to conduct vulnerability assessments, have action plans, create reserves, but all these are half measures. 60 million transformers cannot be protected in a single generation. 12,000 satellites cannot be replaced with radiation-resistant ones in a single decade. 300 submarine cables cannot be inspected and reinforced in a single budget cycle. We built this infrastructure over 70 years ago, at a time when space weather was considered exotic. Now we understand that we live inside the atmosphere of a star, that the Sun is not a decoration outside our window, but an active, unpredictable indifferent neighbour, and that our technological society, for all its power, exists with the permission of this neighbour. Let's return to the figures. The probability of a Carrington-class storm occurring in the next 10 years is about 12%. It's like throwing a dice and hoping it won't land on one. The probability of such a storm occurring in the next 100 years is practically inevitable. And then there are Miyake events, traces of extremely powerful solar storms found in the annual rings of ancient trees. They occur once every few thousand years. They are dozens of times more powerful than Carrington. In such an event, it is not transformers and satellites that are at stake. It is the very existence of electrical civilization. But that's on a scale of millennia. We can think about that later. Now, the next 50 years, the next 10, the next solar maximum. We know that the threat is real. We know how it works. We know how to protect ourselves from it, at least partially. The only question is whether we will have the will to act before the sky lights up again. Because the sun does not wait. It does not plan. It does not warn. It simply burns, just as it burned 4.5 billion years before us. And it will burn for another 5 billion years after us. And we, a thin film of life on the third planet, are learning to live in the shadow of a thermonuclear reactor. And sometimes this reactor reminds us who is in charge here.